So let's talk inequalities. The good news about inequalities is that most of them, on their face, we don't have to think about any differently than equations. When it comes to the process of actually getting a variable by itself on one side of an inequality, and that is kind of the main thing that we're doing for an inequality, solve an inequality for its variable. Most of those steps are the same as they are for solving equations. The only difference, some of the differences, are that some of those differences come in how we express our answers. So this is where interval notation comes in. It's a way of communicating the solution of an inequality in a graphical, not graphical, but also sort of a different way, using a different kind of notation. It's a notation that's going to come back and be a constant. You're going to see it a lot in pre-calculus and calculus. So we get you some practice and some exposure to it now, so that you can focus on what really matters when you're in pre-cal next semester. So let's look at what the ascent up this mountain involves in the realm of inequalities. So at the beginner level, really at the beginner level, the only task is to solve a single inequality for its variable. I'm going to put the word single here in parentheses. Because, of course, when we move to the intermediate level, we end up dealing with multiple inequalities at once. Two inequalities connected by a logical connector, like an and or an or. But we can't do two unless we know how to do one. So let's start with this example. Let's solve this for x. And what I want this to be is, I don't know, 2 minus 3x equals x minus, let's do 1/3. Oops, I put an equal sign in there because my brain is still in first gear here. What I wanted was this. Great, we have to make this an inequality after all. So I want to get the x by itself in this inequality. What are your thoughts? How should we approach this task? So we want to treat this inequality just like we treat equations. So all of our problem-solving strategies for solving equations still apply to this, right? If there are x's, variables, on both sides of the equation, we should add or subtract as necessary to move them all to one side. And we can do that in this inequality by adding 3x. Before I do that, what's a different way that we could accomplish moving all the variables to one side? Instead of adding 3x, what else could I have done here? So instead of moving all the x's to the right by adding 3x, I could have moved all the x's to the left by subtracting x. I'm actually going to take that route because I have an ulterior motive here. Either way will work. But in this rendition, I've got 2 minus 4x now on the left side and negative 1/3 on the right-hand side. Okay, now that all my x's are on one side, what should I do? I got to unwrap this variable. And so to unwrap the variable, we'll reverse the order of operations by finishing all the adding and subtracting that we can do first, and then after that doing any multiplication or division that we need to do to get that x alone. So adding and subtracting first. What should I either add or subtract in the process of trying to get this x by itself? We'll subtract 2 from the left side, subtract it from the right side. So then on the left I'll have minus 4x. On the right I'll have negative 1/3 minus 2, which means we have to do fraction addition or fraction subtraction. I like fraction subtraction because it rhymes. I skipped some steps. We could also have implemented our clearing denominators protocol instead of doing this step. Right? We could have, alternately, multiplied both sides of this inequality by 3 to clear all the denominators. There's only one of them, but still clear that one denominator. And we would end up with something that looks like this. Again, both roads lead to Rome, and so it's just a matter of whether you prefer clearing denominators, which gets all your fraction arithmetic out of the way at once, or going at it straightforward and kind of doing the fraction arithmetic as you go. I tend to like to clear denominators, but that's me. If I didn't clear denominators and I'm working with this inequality right here, what's my last step? Divide both sides by Negative 4. Great. And so that's going to leave me with just x. On the right-hand side, negative 7/3 divided by negative 4 is going to leave me actually with negative 7/12. No, positive 7/12. Negative divided by negative. And my last question is, what happens to this sign? Why?
Because you're dividing by negative.
Yeah, that's why I had an ulterior motive earlier in the problem, is I wanted us to talk about that step, right? We divided by a negative number on both sides, and that's a big red flag, right? Flapping in the wind, red flag. Right. So we divided by a negative number on both sides, and when we do that, the sense of the inequality flips. It reverses. So that now I have x is less than or equal to 7/12. We should double check that if we had cleared denominators, that we also get that same answer. Subtracting 6 from both sides, I'm going to end up with negative 7. I have a negative 12 on the left. And then dividing both sides by negative 12, which again is that big red flag because I'm dividing by a negative. That means the sense of my inequality needs to reverse. Left-hand side is x. Right-hand side is negative 7 divided by negative 12, otherwise known as positive 7 divided by positive 12. So we get the same answer regardless of which way we take here. But the most important bit, I think, in this whole process is the bit that makes it different than solving equations. It's the bit where dividing by a negative number reverses the sense of my inequality. At the intermediate level of this set of skills, we looked at how to take two inequalities and combine them together. And so when we do that, we call it a compound inequality. And compound inequalities come in two flavors. The and flavor and the or flavor. And depending on which flavor we have in front of us, that means that we're going to take the solutions of each of the inequalities and do something different with them to combine them into a single answer. And ironically, that last step is the step that people struggle with the most in this course. Because otherwise, except for that last step, everything we do is the thing that we just did at the beginner level, right? To try and solve the inequality to get the variable by itself. So it's what we do with the and the or that's the part that's going to take you the most thought to grapple with. So let's look at an example. What I'd like to do is, I'm going to put here solve, graph, and then the other thing that we did at the intermediate level was we also used interval notation to express the solution. So we kind of have three things that we're doing here. And let's make this our compound inequality. I want one inequality. Let's say 2 plus 5u is greater than or equal to 8. So there's one of our two inequalities. My second inequality, let's make it negative 3 minus 2u. And then we'll make this greater than or equal to negative 7 or something like that. So here's two inequalities. And I'm going to connect these two inequalities together with a logical connective. So either an and or an or. Let's start by talking about the and. A lot of people, when they're solving these inequalities, will forget to write this word. And then by the time they get done with all the work on each one, they forget that that word is there. And that means that they forget that there's another step to do in the solution. So as we go forward on each one of these steps, I'm going to keep writing and down there in the middle to remind myself that I have to do something with that and before I'm done with my solution. But if we just look at each one of these two inequalities by itself, we know how to solve each of them. That was the beginner level skill. So let's do that rapid fire. Purple inequality. How do I get this u by itself? What's my first step? Subtract. Subtract 2 from both sides. That's going to leave me on the left-hand side with 5u. Right-hand side, 8 minus 2 is 6. And then divide by 5. So I'll have u on the left-hand side. I'll have 6/5 on the right-hand side. What should I do with this inequality sign in the middle? Keep it or flip it? Keep it. Because we divided by a positive 5. We don't have to flip. We shouldn't flip the sense of the inequality. Now, I promised that as we went along, I would retain this logical connective. So I want to hold to that promise. Okay, that's my purple inequality. Let's do the green one. Using the same process that you told me about, we would first add 3 to both sides. And in doing so, leave me on the left side with negative 2u. On the right side, negative 7 plus 3 is negative 4. And our last step will be to divide both sides by negative 2. So that my left-hand side is u, my right-hand side is positive 2, and what should I do with my inequality symbol? Keep it or flip it? So we want to flip the inequality here because we divided by a negative number to get from our second to last step to our last step. So instead of greater than or equal to, I'm going to put less than or equal to. And that means then that so far, what we know about our solution is that we've simplified it into the compound inequality u is greater than or equal to 6/5 and u is less than or equal to 2. But we can't stop there. We need to simplify this conjunction of two inequalities to give us a single answer. And that's the reason why I've written this word graph into the problem. You may not always see it there, but you should always think that it's there, because this, for me, is the step that helps us to do the rest. So what I'll do, and when I say graph here, I mean graph on a number line. What I want to do is graph out what each of these solution sets actually looks like. So u is greater than or equal to 6/5. So 6/5 is a little bit bigger than 1, but it's less than 2. So kind of, actually, why don't I count by 5s here? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so here's my number line. 6/5 is going to be 6 grid squares from 0 now, because each of these grid squares is 1/5. So 1/5, 2/5, 3/5, 4/5, 5/5 is 1. 6/5 then is right here. So 6/5 is this point. And the question is, how do I sketch this inequality on the number line? What's it going to look like? First of all, which side of 6/5 should I be shading? The right side or the left side?
What do you mean?
Should I be shading to the right of 6/5 on my number line, or should I be shading to the left of 6/5? What's this symbol here? How do you read that symbol in words?
Usually u is
Greater than or equal to 6/5. So if I want the numbers that are greater than or equal to 6/5, which side do I shade? To the right. Exactly. You can think of it that this symbol is always going to point in the direction we should shade. So this is kind of pointing as a little arrow to the right. So we're going to shade to the right of 6/5. What about the symbol that I use at 6/5? What should I put right here at 6/5?
Put a circle and shade it.
Yeah, a closed-in circle. And why a closed-in circle?
It's equal.
Right, because u equals 6/5 is actually included in this solution. So we put a closed circle to indicate that. So that's a graphical depiction of the purple inequality. If I put the green inequality on here as well, which side of 2 do I want to shade, first of all, left side or right side?
Left side.
Left side. Because here we want the u's that are less than or equal to 2, so I'm going to shade to the left. And what symbol at 2?
Same as the other.
Same as the other, closed circle, because less than or equal to includes the number 2. So there are my two inequalities, and I need to combine them together into one, and this is where the connective comes in. This is where the word and is important. So what does and tell us to do with these two sets in order to produce one set, which is our answer? I'm looking for the numbers that are both greater than or equal to 6/5 and simultaneously less than or equal to 2. Where am I going to find those numbers on the number line? if I need to belong to the purple set and the green set at the same time, where must I be?
You're in between like 1 6/5 and 2.
Right. So I need to be in a place where both the green and the purple are shaded. Right. I can't be a number less than 6/5. I can't be over here, because then even though I satisfy this inequality, I don't satisfy that one. Likewise, I can't be anything greater than 2 because I would satisfy the purple inequality but not the green. When the word and appears in this connective, it means that we must satisfy both inequalities. And so what we're looking for is we're looking for the overlaps of these two intervals. And that's where I think the picture really does help, right, to know that we're getting the right combination. If I take these two intervals and I look at where they overlap, I'm going to find out that they only overlap for those numbers between 6/5 and 2. So my overlaps are right here. What about the ends? Do I want open circles or closed circles?
Will it be closed?
Closed circles, right? Because again, the number 6/5 does belong to both sets, and therefore it should be in our answer. And the number 2 belongs to both sets, so therefore it should be in our answer. And so our final answer is going to be that red set that we just shaded. And all we have to do now is figure out how to rewrite that final answer using interval notation. So that's our last task here. How do we write interval notation for this red set? What goes into interval notation, by the way? What do we need to know? Right, so one thing is this an interval that goes out to infinity on one side or not? What about this one? Does this red interval go out to infinity? No, it doesn't. It's what we call in mathematics a bounded interval. So that means that we need to supply it with what is its left-hand lower bound and what is its right-hand upper bound. What is the left-hand endpoint of this red interval?
The end of it is 2.
The right-hand end of it is 2.
Oh, right.
So that means that I'll put a 2 right here on the right side of my comma. The left-hand endpoint?
1 6/5.
Yeah, it's actually just 6/5, but yeah, 6/5. So that's going to be my left-hand endpoint. So now I've supplied the two endpoints. Now I just need to supply some notation in my interval notation that says whether these endpoints are open or closed. Given that both of my endpoints are closed, what symbol should I put on either side of this interval? What symbol do we use to indicate that 2 and 6/5 are both included in this set?
Would you put 2 lines next to both of them?
Yeah, and specifically, those lines should be square brackets. So these square brackets indicate that 6/5 and 2 are both included in my final answer. They also square brackets always go along with filled-in circles. Anytime there's a filled-in circle on your graph, you know that you're going to have a square bracket at that point in your interval notation. And so I would consider then this to be our final answer for this problem, right? We started with this compound inequality, we solved it, we graphed it, but then our final answer to this inequality is this notation that tells us the set of all real numbers between 6/5 and 2, which is inclusive of both the left-hand endpoint at 6/5 and the right-hand endpoint at 2. This was the case for and. Let's rehash it for or. Let's imagine that we had or in this problem instead of and. So I'm just going to wipe out my ands, replace them with ors, but leave everything else the same for the moment. So when we did the and, we were looking for the overlaps. When we do the or, something's different. So let me also wipe out my red set from over here. That was our final answer. Try and clear that away here. Okay. So let's think about what we would need to do differently for an or. What's the difference between the words and or in English? What does or make you think of that and doesn't? The word or gives us a choice. And the choice thinking logically about these two inequalities, the choice is that the numbers in my solution can either satisfy the purple inequality or satisfy the green inequality. Or they might satisfy both, but we have the choice now. All right? The numbers that before satisfied only one and not the other, those were not a part of the and, the conjunction. Right? A number like 3 or 0. Right? 0 satisfies only the green inequality and not the purple one. So it wasn't a part of our and. But because or gives us a choice, it will be part of the or. So it must satisfy one or more of the inequalities. So one or both. So instead of looking for the overlaps, what we're really doing here is we're kind of gluing all together. Any place where either of our intervals goes, that will be where the or lives. I don't have much space. Together. There we go. So we're going to take, as part of our answer, everything that belongs to the green set, but also everything that belongs to the red set. We're just going to stick them all together, throw them all into one big bucket. And if I do that, I end up shading a whole lot of the number line. So let's think about what interval notation would look like for this set. How far to the left is this red set going to go? As far as it can go, because after all, that's how far left the green set goes, right? Yeah. So what would we say is the left-hand endpoint for my interval notation for the red set? And because it's the infinity on the left side of the number line, yeah, we call it negative infinity.
2.
And then likewise on the right side, how far to the right does this set go? That's right, it goes as far to the right as the purple set goes, namely positive infinity. In other words, this red set is actually shading in every single real number on the number line. Every single real number on the number line satisfies one of these inequalities or the other. What about the notation in this? Square brackets, round brackets, what should I use on these minus infinities and plus infinities?
6/5,
Is negative infinity included in my solution, or is it not included in my solution? Well, negative infinity isn't a number.
It's included, but like you wouldn't do the square ones because it's not bound.
Yeah, you can think of it that way. So negative infinity, negative infinity itself is not a number. We can't actually include it in a solution. So you should almost have a knee-jerk reaction about infinities in your interval notation, in that infinities are always accompanied by round brackets. Because they're not numbers, we can't include them in our solutions, and so we use round brackets to indicate that. So where we go next with this? This is why I think the inequality unit is so profoundly challenging, is that even the intermediate level takes a lot of thinking and reasoning to wrap your heads around. And so at the advanced level, we're bringing one more thing into the mix. And that one more thing is to solve an inequality that includes an absolute value. And just like with some of our previous climbs up the mountain in this review, the key to solving an absolute value inequality is going to rely on us translating it into a compound inequality that we then know how to solve because we just did that. And that then requires your beginner level skills. So these really do build one on another. This is typical, it happens in any math class. And so we're just trying to make it as explicit as possible how as we go through this material one more time. And so as you're practicing and preparing for the next run at the exam, the way your homework packets are set up is that the first couple questions in your packet target the beginner level skills. So start there. Make sure that you can walk before you can run. And make sure that you can run before you can sprint. Or do a marathon, or whatever you want to use for the metaphor here. So now that we've learned the intermediate level skill, let's talk about what else we need to get to that advanced level. So let's start with a simple example. I'm going to take the inequality thing out of the mix for a moment and just talk about absolute value. So let's suppose that I say solve the equation absolute value of x is equal to 8. How do we think about that? What does absolute value mean? So what the absolute value of a number measures is it measures how far away from 0 that number is on the number line. So for example, if I have the number 8, how far away from 0 on the number line is 8? How many units of distance, if you like? Eight units of distance, right? The number 8 is 8 units away from 0. And so what we would say is that the absolute value of the number 8 is equal to 8. That's that distance. But can you think of another number whose absolute value is also 8? What other number is also 8 units away from 0? Negative 8. 2, 3, 4, 5, 6, 7, negative 8. Right. So one of the reasons that absolute value shows up in discussions about squaring is that just like with squaring, there's this sign ambiguity that happens with absolute value. That both 8 and negative 8 have the property that their absolute value is the same. Their absolute value is equal to 8. So sometimes the way that people think about it, what absolute value does, and one way of defining what absolute value is mathematically, is it leaves positive numbers alone. And it takes negative numbers and it flips them to positive. Right? So it kind of throws away negative signs in front of real numbers. Right? And 0 it would also leave alone. Right? So the absolute value of any positive number is just equal to that number itself. The absolute value of any negative number is equal to the opposite of that negative number. So all absolute values come out to a non-negative answer. Why? Because they're measuring a distance, and distances are always non-negative quantities. So if I want to solve the equation, absolute value of x equals 8, what values of x solve that equation? According to our picture, 8 solves it, but so does negative 8. And one of the takeaways from that is that when an absolute value goes away, when absolute value disappears, it leaves behind a plus or minus. Right? So when I remove the absolute value bars from this equation on the left-hand side, the plus or minus pops up on the other side. This is really valuable to know. And we were talking about squares a moment ago. That's one of the reasons for the plus or minus symbol in the quadratic formula. It's going to be the last thing that we learn this semester. We're going to talk about it next week. No, 10 days from now, 11 days from now, 12 days. The next Monday that we're in class is when we'll talk about the quadratic formula. But the reason for the plus or minus there is because it is the unwrapping of an absolute value. Because the absolute value throws away negative signs but it leaves the positives alone, there are almost always two answers to an absolute value equation. So that's what happens on the equation side. But when we start to stick inequalities into the mix, things get a little bit more interesting. So let's tweak this example so that instead of an equal sign, I have, I don't know, less than or equal to sitting in here. So absolute value of x is less than or equal to 8. So now we have to think about what this actually means. So I want to actually write it down in words, thinking about distance. What we're saying is that this is the set of all x whose distance from 0 is less than or equal to 8. That's what that inequality means when you unpack the meaning of an absolute value. So one of the ways to go about this, there are a variety of schools of thought on how to solve absolute value inequalities. One of those schools of thought is to first solve the equality. I don't know that this is the way that we're going to take, but let's try it. So solve absolute value of x is equal to 8, and we just did that, right? x equals 8 and x equals minus 8. And then we plot those two values on my number line. And then in this school of thought, we would then test numbers. So on my number line, what I would need to do is I would need to test one number that's less than my smallest solution. So I would take a number like -9 and try it. I would need to test some number that's in between my two solutions, let's say 2, plug it into the inequality and try it. And then take a number that's bigger than my biggest solution, like 10, and try it. Right? And anytime I get a hit, anytime I get a yes, I'm going to shade that whole piece of the number line. Anytime I don't get it, I won't shade that piece of the number line. So in that approach to it, what we would do is say, is it true that the absolute value of 2 is less than or equal to 8? Is it true that the absolute value of 10 is less than or equal to 8? And is it true that the absolute value of -9 is less than or equal to 8? Of those three inequalities, which one of those three is actually true? It's actually only this one here in the middle. Because what is the absolute value of 2? It's 2. And 2 is, so the only one of those three that actually is satisfied is the one in the middle. And then what that means for us is it means that we can shade that whole piece of the number line that test belonged to. But the ones that are false, those are places that we can't shade. Then we would specifically test the endpoints themselves to see if we need to include those points as well. Is it true that the absolute value of 8 is less than or equal to 8? Yeah, it's true. Because both sides of that inequality are 8 and it's less than or equal to. Same thing happens on this side. And so then we would have our sketch on the number line. Then we would just express it as interval notation. And in interval notation, that would be the closed interval from -8 to 8, square brackets. So that's one approach to go about this. But it's not a very, I don't know, to me it feels cumbersome to actually implement this approach. So I actually prefer an approach that lets us connect back to what we know about compound inequalities. So let's talk about that one, and that's how we'll round out this, this set of examples. Here's an inequality. Twice the absolute value of 3x plus 1 is less than 26. How are we going to make progress on this? Well, the first thing that I'm going to want to do is to try and get it so that the absolute value is the only thing on one side of the equation. And the thing that's preventing that is this 2 that's out front. So how could I get rid of this 2 from the left-hand side? Because 2 is multiplying this absolute value. If I want to get rid of it, I should just divide both sides by 2. If I do that, then my new inequality is just absolute value of 3x plus 1 on the left. And on the right, 26 over 2, 13. Okay, so now I have just an absolute value on the left. And so now is the time when we can talk about what to do with an absolute value inequality. If I have an absolute value on the left-hand side and a less than, I actually end up doing something different than if I have an absolute value and have a greater than. So this is something that is also a little hard to keep track and will require some practice. In the case where I have a less than sign, what I end up doing is I end up getting a compound inequality with an and in it. And as you might expect, with a greater than, we end up needing an or instead of an and. And then you say, well, anding and oring what? Because in our compound inequality work at the intermediate level, we had 2 different inequalities that were connected with this and or this or. So we have to say what those 2 inequalities are. And here, again, is a place where when the absolute values disappear, we end up with a plus or minus showing up. So here's how it looks in inequality land. We take the absolute value away, and so we get 3x plus 1 without the absolute value in it. On the right-hand side, we have a 13, and when I write my new right-hand sides, one of them is going to be positive 13, and the other one's going to be negative 13. So that's where my plus and minus shows up. It's going to show up in kind of two different places here. Because this inequality had an upper bound, this absolute value had an upper bound, we're going to use an and to connect the two of those together. And then the last thing, as though to make things even one more step to remember, the inequality signs I'm going to put here are also opposite to one another. So when I keep the 13 as it is, I'm going to keep the inequality symbol as it is. So when the 13 stays, so does the less than. But when the 13 flips, the inequality is going to flip as well. So notice this is the step, this is the hard step, right, in solving an absolute value inequality, is splitting the inequality apart and then figuring out how to either keep or flip the signs that you get. So the signs flip when the sign flips. So when the 13 becomes negative, the less than becomes greater than. And when the sign remains the same, the inequality remains the same. And the other piece of that is, do we get an and or do we get an or? And that depends on whether we had a less than or a greater than. It would work the same, by the way, if it were less than or equal to or greater than or equal to. What matters is the direction of the inequality and not the inclusiveness. So now we have a compound inequality to solve. And so from that point, we plug in our intermediate level skills, which I'm going to try and go through quickly. So let's plug in our intermediate level skill, which requires us to solve each of these inequalities. So I'm going to subtract 1 from both sides, and then divide by 3. I'm going to try to skip writing the intermediate steps here. If you're solid with your beginner level skill, you'll know what those intermediate steps are. So that the inequality on the left, I'm going to make them purple and green again, is going to be x is greater than negative 14 thirds. And the inequality on the right is going to be x is less than 12 thirds, which is 4. And then I have my connective in the middle, the word and. And so now we plug in our sketching skills that we used at the intermediate level. I'm going to try and shrink this little bit here to move it off to the side. So we'll put in our number line and our purple inequality, which is x greater than negative 14 thirds. So negative 14 thirds is somewhere over here. It's negative. That's all we really need to know about it. Shading to the right, and I'm going to have an open circle because this is just less than, not less than or equal to, negative 14 thirds. And then x is less than 4 is my green set, and 4 is greater than negative 14 thirds, so it's going to come from up here and shade to the left. And an open circle up there again because it's less than and not less than or equal to. And if I'm anding these two sets together, what am I looking for? How do I combine two inequalities with an and? And these two sets together, I'm only going to be looking for their overlaps. And the overlaps only exist right there. With open circles or closed circles? Open circles, just like they were in the original sets, because negative 14 thirds is not included, and 4 is not included in their respective sets. They're not included in the intersection either. So what would be interval notation for my solution? What's my left-hand endpoint for the red set? Negative 14 thirds. My right-hand endpoint for the red set? What kind of brackets, round or square? Square if we want to include these values, round if we want not to include these values. Open circles mean that we're not including those values. So open circles always go with round brackets. And then that would be my solution. So the key to solving an absolute value inequality is to turn it into a compound inequality. Right? Get the absolute value by itself, and once that's by itself, we can use this little idea over here to turn it from one inequality with an absolute value into two inequalities without an absolute value but connected by either an and or an or, depending on the direction of the original inequality. That's a mouthful. This is the step that you want to make sure that you're solid on. Right? Because once you take that step, The rest of it is our intermediate level skill to solve a compound inequality. Solve each one, plot them out on a number line, and then use your connective, whether it's and or, to combine them together into a single answer.